guess this should be it. Okay, so let's start. So this week we're gonna talk about equivalent circuits. Okay, what is all that? The Thevenin theorem, the Norton theorem sounds very scary, but don't worry. So the main question that this chapter asks is this: can I make a simplified version of a very complicated circuit? Okay. In the lectures, right, in the pre-recorded lectures, Prof. Domenico said something about like a super complicated circuit, then he represents it with a cloud. So this is what he means. It's a super complicated circuit. And then the main question that this whole chapter is trying to ask is, can I make a simplified version of this circuit? And the answer is yes. Okay, so let's move on. So if I can, then how would it look like? Okay. Now here's where we split into two ways. See? The first way is the Thevenin equivalent, right? The Thevenin equivalent of a circuit. The other way is the Norton equivalent. Now, what's the difference between these two? The Thevenin equivalent is that if I can simplify the circuit, and if I imagine this circuit to be driven by a voltage source, then it would look something like this. So this is my Thevenin equivalent. So this is V Thevenin, like that. This is my Thevenin resistance, like that. It's in series. So these are the two terminals we are looking through. Okay, so again, I have a super complicated circuit. Can I simplify it? Yes. If I simplify it, if I imagine this circuit to be driven by a voltage source, it will look like this, called the Thevenin circuit. Okay, there's a message. Let me see what is it. Yeah, of course. Otherwise, what's the point of me recording it, right? Okay. Next, the Norton equivalent. So the Norton equivalent is this. If I simplify the circuit and I imagine it to be driven by a current source, what would it look like? It would look like this. So instead, I have a, sorry, let's not do this. This is the Norton current source, the equivalent current source. And then it is in parallel with the Norton resistance, A, B. So see, we know there are two things that can drive a circuit, right? Which is either a current source, a voltage source or a current source. And that is what the Thevenin and Norton is. If I simplify it and then I view it with a voltage source, it will look like Thevenin. If I view it with a current source, it will look like a Norton. Okay, that's it. Now, having said that, the next question is how to find first the Thevenin equivalent. So this is the important part that you should note down. Okay, if it helps you, please write these. Please jot down these steps in your lecture notes or wherever, and put it in your memory. So, number one, the first step to do is find the open circuit voltage. This open circuit voltage is the V Thevenin, okay, the Thevenin voltage. Number two, find the closed circuit current. Or actually, sometimes we call this short circuit current. Okay, properly it's called short circuit current. Short circuit. Okay, number three. Okay, this one we label it as ISC, current short circuit. Okay, ISC is current short circuit. And lastly, to find the Thevenin resistance, you take the first two answers from here and here, you just divide them, right? So V Thevenin divided by I short circuit. Done. Okay. Once you have these three values, then you can draw your Thevenin equivalent resistance or Thevenin equivalent circuit. So here's the voltage source. Here's the in series with your resistance, your Thevenin equivalent resistance. And then these are your two terminals, A, B. And that's it. So please note down these 3 steps. Put it in your lecture notes or wherever, because this is the most important working in this chapter. Okay, this very very important. Okay, I'm gonna repeat again. First, open circuit voltage. Second, closed circuit current. Third, using the answers from the step 1 and step 2, you just divide. Okay, so to find the Thevenin resistance, you take V over I, right? Looks like Ohm's law because it is. So V over I, and you get your Thevenin resistance. Then when you draw your circuit, make sure the resistor is in series with the voltage source. Okay, series with the voltage source. Never mind if this doesn't make sense first. I just want you to remember the steps. Open circuit voltage, short circuit current, then the first answer divided by the second answer. Okay, keep this in your mind and keep this with you until your finals, because this is essentially it. Open circuit voltage, closed circuit current. Take the first answer divided by the second answer. Okay, got it? Now, the Norton equivalent, I tell you what, once you know this, right, the Norton equivalent, finding the Norton equivalent is literally 2 seconds away. Once you know this whole method, you're 2 seconds away from knowing how to do the Norton equivalent. So with that, let's do an example, right? So, prepared an example. Okay, let me just do this. Hold up. Okay, haha. Okay, number 1, find the Thevenin equivalent of the circuit. Find the Thevenin equivalent circuit as seen by the resistor labeled A. Now, the thing that I draw just now was the resistor labeled A. So what does that mean? Remember, number 1 is, what's the first step? Can anyone tell me in the chat? What's the first step? What's the first step? Remove the load. Yeah, okay. Okay, so what I said just now is find the open circuit current. Open circuit voltage, right? Step 1 is always find the open circuit voltage. Then, okay, so what does it mean? If I want the Thevenin equivalent of this resistor labeled A, and I want the open circuit voltage, right? Open circuit means I have to remove the load. I have to remove the resistor A. So if I want the equivalent resistance seen by A, I need to remove A first. That is finding the open circuit voltage. So I'll erase A away. See? Because there's nothing here, this is the open circuit. And then what does it mean by the open circuit voltage? So the open circuit voltage means the potential difference between these two terminals, this and this. The voltage difference here is the open circuit voltage, otherwise known as the Thevenin voltage. Okay, this is the Thevenin voltage. You remove the load, that's an open circuit. And that open circuit voltage is the Thevenin voltage. So we need to find that. How to find that? That's why we need to be strong with our methods from last class. You remember we learned about mesh current, node voltage? So this is what we're gonna do. We're gonna either use mesh currents or node voltage to find the potential difference across A and B. So you can choose literally anything you want. If you want to choose node voltage, that's fine. If you want to choose mesh current, that's fine. In this case, I would choose mesh current. Why is that? Because there's only 2 meshes I have to deal with. If I choose node voltage, right, I have to deal with 1, 2, 3, possibly 4, because okay, this is 0. But you see, there's more nodes I have to take care of rather than the number of mesh. In this case, what's the mesh? It's this one, right? A, and then this one, B. See, I only have 2 meshes to deal with. So of course, the preferable choice is mesh currents. So let's go ahead and do that. So remember, mesh current method means we have to use Kirchhoff's voltage law. So let's look at Kirchhoff's voltage law. Sorry, it's my mouse. Okay, sorry, I'm gonna write here. So KVL at A. Okay, so KVL means we start from a point Okay, start from any point, and then we walk around, we add up all the potential difference. So let's start. We walk through here. This is a potential gain, right? I'm going from the negative to the positive. Negative to positive, lower value to higher value. So potential gain means positive. So positive 72. And then I go through here. But you see, the current through this resistor, it is not IA. It is IA minus IB, right? Because the net potential, sorry, the net current rightwards must be IA, which is going rightwards, minus the IB, which is going this way. Okay, so it's IA minus IB minus IA minus IB multiplied by resistance. Then I go down here, which is minus IA times 20. Then I come back to the start, so nothing, so just equate it all to 0. Oh yeah, keep in mind, over here, this is not a mesh. Why? Because there's no wire closing this, right? It's not a mesh. So there's no mesh current over there. Then if you simplify this, you expand, you simplify, you should get 25 IA minus 5 IB equals to 72. Okay, so this is our first equation. Label this equation 1. Next we do KVL, same at B. So KVL at B is okay, so we start from anywhere. Just choose any point. So let me start here. I go through this. So resistor is a potential drop, right? Resistor is potential drop, so it's negative. Negative IA, oh sorry, IB multiplied by the resistance is 12 ohms. Next, I go through, where am I? I go through this already. Now I go through the 8 ohm. So minus IB times 8. Then, now, when I go through here, the current is not only IB, it is IB minus IA because it's between the mesh A and mesh B. So it's IB minus IA. So minus IB minus IA times 5 equals to 0, right? Then you expand and simplify, you should get negative 5IA plus 25IB equals to 0. Okay? So 2 equations, 2 unknowns. This can be solved. Again, press your calculator. I hope you got your calculator. In case you haven't, please go to book link tomorrow. So if you solve this, solve 1 and 2, you should get IA equals to 3 and IB equals to 0.6. Now, remember we are looking for the open circuit voltage. Don't forget our motive. Our motive here is to find the open circuit voltage, right? But I found the currents. So how do I find the potential difference across these 2 nodes using the circuit? Well, the answer is like this. You know that here and, well, here. Okay, actually, keep in mind, this whole thing down here, where I'm highlighting over here, this whole thing is a node, right? Because check, is there any devices across there? No, there's no devices, so no potential difference. That means this whole thing, this segment of wire down here is a single node with a value of B, right? It's a node. It's a node whose voltage value is B. Now, to get the potential difference across A and B, what I can do is I look at the potential drop across this 8 ohm, and then the potential drop across this 20 ohm. If I sum them up together, I will get the potential difference across A and B, correct? Okay, I'm going to repeat that again. From here to here, this is 1 voltage difference. Then from here to here, through the 20 ohm, this is another voltage difference, so 20 ohms, right? If I sum these 2 potential difference, that would just give me the sum of, that would just give me the potential difference across A and B, correct? Okay, I hope this is clear. Is it clear to everyone? Hope so. Okay, I assume it's all right. So having said that, let's go ahead and do that. So the Thevenin, which is the open circuit voltage, is given by the 8 ohm potential drop. Let me just put delta to show potential difference, right? Plus the potential drop across the 20 ohm. Now remember, delta V equals to I times R. So what's the I across the I through the 8 ohm? The I through the 8 ohm is IB. IB is 0.6. So this is 0.6 times 8 ohms plus, now what's the current through the 20 ohms? Current through the 20 ohms is IA. IA we found just now it is 3. So 3 times 20. Now if you do this, your Thevenin should be 64.8 volts. So this is the potential difference provided by the voltage source of the Thevenin voltage source. Okay. So step 2. Now what's our step 2? Step 2 is find the short circuit current. Now what does that mean? Short circuit current. So let me clear everything that I do here. Short circuit means I close it with a wire, right? It's just the opposite of opening a circuit. Opening a circuit means I cut the wire and then now it's disconnected. Short circuit means I just stick the wire back together. So I short it out. So that's what shorting means. So let me just short A and B. That's what it means. So short circuit A and B. And we want to find the current through this now. Okay, let's call this I short circuit. So what do? I just use mesh currents as well. So this is IA, this is IB, and this is IC. Now, in your exam or your quiz, right, please redraw this whole thing and then, there was a resistor here, right? Yeah, just remove the resistor and then connect it with a line. And just now for the open circuit one, just draw everything and exclude the resistor. Please don't be lazy, just draw everything out. It doesn't take you more than a minute to redraw everything. Because when I was a student, when I tried to just use the diagram, yeah, I made a lot of careless mistakes. I was very confused. So don't be lazy. Learn from my lesson. Just do everything out. Don't make careless mistakes. So let me just check the chat. There's something notification. Okay, it's just people participating. Okay, very good. So let's just solve the equations. Okay, so let's do mesh current again. So mesh current. So in IA, we have 72. So KVL at A. So okay, positive 72 minus 5. Okay, IA. Okay, IA minus I. Wait, let me just stick to last time. Okay, sorry. This is IB. This is IC. So is IA minus IB times 5. IA minus IB times 5. Anything else? Minus IA minus IC, correct? See, the current going through here is IA, which is this one, minus IC, which is trying to oppose us, right? IC is trying to oppose us. So it's IA minus IC. So minus IA minus IC multiplied by the 20 ohms. And that's all, right? Yeah, that's all. Equals to 0. Expand and simplify this. You should get, okay, 25 IA minus 5 IB minus 20 IC equals to 72. So this is our first equation. Now let's go to mesh B. So sorry, to prevent myself from scrolling up and down, right? Let me just drag this picture down. So silly, I should have taken the whole picture. Okay, wait. Sorry. Okay. Better. Okay. So we're trying to solve IB, right? So KVL at B. So let's start from here. We go to here. So negative because it's a resistor. Resistor is voltage drop. minus IB times 12. Then I'm going to where? I'm going to here. So it is minus IB minus IC times 8 minus oh dear, I don't have enough space. What is this? IB minus IA times 5. And then we come back to the red dot, so equals to 0. Expand and simplify this, you should get 5 IA plus 25 IB minus 8 IC equals to 0. Right? So this is our second equation. Now, let's go solve mesh C. Or KVL at C. Sorry. KVL at C. So let's start from here. So when we go to here, this is I minus IC minus IA times 20. Then we go to here. This is minus IC minus IB times 8. Then we go to here, which is nothing. We go to here, which is nothing. So we come back to the start. This is equal to 0. Expand and simplify this. You should get, what should you get? Okay, you should get minus 20 IA minus 8 IB plus 28 IC equals to 0. Okay, now this is your third equation. Three unknowns. Okay, punch it in your calculator, solve 1, 2, and 3. You should get, what is it? You should get IA equal to 12.72, IB equals to 6.00, IC equals to 10.8. Okay, don't forget our objective. What is our objective in the second step? The second step, we want to find the short circuit current. What is the short circuit current? It is actually IC, right? You see, this is the current we want is the current through this. And IC is going through that branch, correct? I hope you all can see that. See, IC is going through this branch. And that is the branch we want. That is the current that we want, which is this one, flowing through the wire between A and B, which is the short circuit current. So actually, we don't even need these two, right? We don't need this. We don't need this. The most important character in this story is IC. Okay, so based on this, we know that I short circuit is 10.8 amperes. Now, remember, what's the final step? We want to find the Thevenin resistance. So the Thevenin resistance is given by V Thevenin divided by I short circuit, which is equal to, now, earlier we got 64.8 volts, then later we got 10.8 amperes. If you divide this, you should get 6.0 ohms. Now, what is the Thevenin equivalent resistance? What does the Thevenin equivalent circuit look like? It will look like this. It should look like a voltage source in series with the Thevenin resistance. And then this is the terminals A and B just now, right? We are looking through A and B. And this one we label as 64.8 volts, and this one we label as 6.0 ohms. 6.0 ohms. And that's it. So follow the steps religiously, okay? I'm going to recap again. Number 1 is open circuit
including
voltage, okay? Open circuit voltage. This one is the V Thevenin. Number 2 is the short circuit current, or the closed circuit current. And this is the ISC. Number 3, you just take the answers from step 1 and step 2 to find the Thevenin resistance. Follow these steps religiously and done. We're done. Now, the next question is find the Norton equivalent circuit as seen by the resistor. Now, again, I'm going to say it again. Once you know the Thevenin, how to find the Thevenin equivalent circuit, right? You are literally 2 seconds away from finding the Norton. Why? Because let me show you what are the steps to find the Norton equivalent of the circuit. Okay, wait. So, ladies and gentlemen, to find the Norton equivalent of the circuit, right? Norton equivalent steps. So how to find that? Done. Okay, it's the same thing, except now you need to acknowledge that this one is I Norton, right? The short circuit current here is the Norton equivalent current source. Okay, see, it's the same exact steps as what we did just now, except now think of the I short circuit as the Norton equivalent current source. And then, right, here's a fact that you need to know. The Norton equivalent resistance is, in fact, the Thevenin resistance. Yes, they're the same thing. They are the same thing. Norton and Thevenin, the resistance are the same because they represent the total resistance of the circuit. So it doesn't matter if I took away my current source, I change it with a voltage source, the resistance isn't changed, right? It's the same thing. So Norton and Thevenin, the resistance are the same. That means this, right? Instead of R Thevenin, I could just call this R Norton. And these things are the same. You still use the open circuit voltage to divide by the short circuit current. Or I can think of this as IN right now, right? So it's the same thing. Now with that, what do we have? We want the equivalent. We already found the values of the I short circuit, right? I short circuit just now was 10.8. So which means this is in fact our Norton equivalent current source. Okay, this is our IN. And then just now, we already found the Thevenin resistance earlier, right? Which is 6.0 ohms. So this means our Norton equivalent resistance is 6.0 ohms. Correct? Now with that in mind, we just need to draw it properly. Now how to draw it properly? It is a current source parallel to the resistance. So this is R Norton, which is 6.0. And then this is the terminals A and the terminals B. And then this one, just now I said is
it's about
10.8
right?
10.8 amperes.
Yeah, I'd like to ask you guys.
Okay.
Would you all be generally available?
So yeah,
Sunday.
please. The most important thing at the end of the day is these 3 steps. This. Okay. Okay. Moving on. Now the last question. So I can cover this maximum power transfer. So let's go back to our simplified circuit. Of course, we can simplify the circuit, right? We can simplify it either to the Thevenin equivalent or the Norton equivalent. At the end of the day, it is still a circuit, right? No matter if it's complicated or simplified, it is still a circuit. And what do circuits do? Circuits consume power. So maximum power transfer means what is the power consumed by the simplified circuit? Okay, what is the power consumed by the circuit? So to find the max power transfer, you just remember this formula. So power equals to V Thevenin squared over 4 times R Thevenin. Just like that. Remember this formula and all will be done. Yeah, I think Professor Domenico went through a derivation, right? But no, that's too time consuming. It's more efficient just to remember this, right? In fact, it kind of looks similar to the V squared over R, except I plug in a 4 here, right? Right? I just plug in 4. Okay. So V Thevenin squared over 4R Thevenin.
Yes, do the 5.
Then this will be the max power transfer. So this is max power transfer. So I already have the V Thevenin, which is 64.8 squared, 4 times the Thevenin resistance, which is 6.0. I calculate this. I didn't calculate this, but yeah, punch in your calculator, you should get it. Okay. And of course, the answer is in watts. All right. So that's all you need to know. This formula and the 3 steps that I showed you. And you need to know for a fact that the Thevenin and the Norton resistances are just the same. Okay, it's just the same thing. And of course, remember the configuration of the Thevenin resistance. So Thevenin is in series, right? This is series. But Norton is parallel, right? These are parallel. Okay. So let's try another question. Okay, here I ask you for the Norton equivalent, but if I ask you for the Thevenin equivalent, it's not a 1 minute away job, right? So let's go ahead and do that. So recap again. Anyone tell me in the chat, what's the number 1 step? Step 1 is find the open circuit voltage. Thank you, Samuel. Open circuit voltage. So let's go ahead and do that. See, the question already opened the circuit for us, right? If they want to, like just now, they will put a device here.
Yeah, that's what I was thinking.
Then they'll say find the Norton equivalent as seen by the resistance as the resistor labeled A or B or something like that. Okay. Then what you do is you need to open it. So just remove it. Okay. Find the open circuit voltage. So let's just do mesh currents. Okay. Just do mesh currents first. So here, IA. Here, IB. Let's do KVL. KVL at A. So we go to here, nothing. We go to here. Oh, sorry. Okay, what am I doing? Okay, want to do a KVL at mesh A. Okay. Oh, okay. I don't know, I had a brain fart. Okay, see, IA is at the same mesh as the current source, right? So that means IA is equals to 9 amperes. Yeah, I don't know why I was silly. Okay, IA, because IA is this mesh current, right? And then in this mesh, we happen to have the current source. So that means IA has to be 9 amperes. Okay, my bad. Don't know why I was not thinking there. Okay. Now let's do KVL at B. So we start from here. So we do this. So this is negative IB minus IA times 12. Then we go to like this, minus IB times 2. Then minus IB times 9. Then go to here. This is IB times 4. Then we start back, so we just equate it all to 0, right? KVL. So if you expand and simplify, simplifies. So let me check my working, huh? Oh, wait, I did a different question. Sorry. Sorry. Hold on, hold on. Oh, sorry. The working that I prepped for, right, was for this different question. So like that. Let me just draw this out. I'm very sorry. Plus minus. Like that. This is 40 ohms. This is 10 ohms. This is 8 ohms. This is 60 volts. The previous 2 questions, I just gave it for you for extra exercise, okay? I don't know if I have enough time to go through it or not. Okay, this is A and this is B. So we want the Norton equivalent as seen by A and B, right? So again, I find the mesh current through this. Oh, and not through this, right? You cannot find there's no mesh current here because this is open. Okay, so KVL at A. So let's start from here. We go to this is a positive 60 because it's a voltage gain. We go from the negative to the positive terminal. Then after that we go to here. This is minus IA times 10. And then this one, this is minus IA times 40. And then we go back around, so it just equated to 0. Right? So this is only one equation and one unknown. If you solve for IA, you should get 1.2 amperes. Okay? So the second step, can anyone tell me what's the second step? We need to find the what? We haven't found it, right? Sorry. We haven't found the open circuit voltage, right? So don't be in a rush first. Now, the open circuit voltage is the voltage difference between A and B, correct? So we want the potential difference across here and here. Now, how do we do that? Using this IA. Now, you have to notice this one thing. Let me ask you this. Is there any current through here? I mean, current through this branch and the bottom branch down here. Any current? No, right? Why? Because it's an open circuit. It's an open circuit, right? There's nothing here, so it's an open circuit. No current can flow through. Now, what that means is there's no potential difference across this whole terminal, right? Because if there's no potential difference, then there's no current. Oh, sorry. If there's no current, that means there's no potential difference. That means the whole top is the same voltage value. Okay? Same voltage value across this whole top. So if I can find the current, if I can find the voltage drop across here, across these two nodes, this one and this one, it will be the same as the current, sorry, the voltage drop across A and B. So this VAB, sorry, Thevenin, is the same here. So this is also Thevenin. Okay? Because there's no current through here, so there's no potential drop. These two are the same. These two are the same. Also same here. No current here, so that means these two are the same. Okay? So let's try to find the potential difference across this resistor then. So how to find the potential difference across this resistor? Use the formula delta V equals to I times R. What's the I through the resistor? It is this IA. IA is 1.2 and the resistance is 40 ohms. Find that, you should get, so Thevenin, this is actually our Thevenin, right? Which is 48. Yeah, 48 volts. Okay, second step, can anyone tell me? We need to find the what? Woo. Find the what voltage? Tell me. Come on. Short circuit current. Thank you. Okay, thank you, Vishnu. So short circuit current. What does that mean? That means, so let me just erase all my annotations. Here. Let me be quick. Like that. Ooh, oh my god. Like that. So short circuit means I close the terminals. Okay, I close the terminals. I close it from here to here. Now I need to find the short circuit current here, ISC. So again, just do another round of mesh current analysis like that. And then now there's a mesh current here because it's closed. So this is IA, this is IB. Let me just bring down this whole. This is gone already. This is gone already. So let me take a picture of this. Oh, actually, the middle is 40 ohms. Okay. So this, and this is 40 ohms. So let's do KVL again. So Kirchhoff's voltage law at A. So at A, we have this, which is plus 60. Then go to here, which is minus IA times 10. Then to here, which is minus IA minus IB. Don't forget, okay, IB is opposing us, times 40. Then we go back. So equated to 0. Expand and simplify, you should get
relevant to what's relevant to what we do now or radically different.
okay, you should get minus 50 IA plus 40 IB equals to negative 60.
Does it need to be like somewhat
So this is your
radically different?
first equation. Next, we want to do the KBL at B. So let me just do it over here. And this is answer in the chat. Let me see. Short circuit current. Okay. So KVL at B. So again, start from anywhere you want. So let's just start here. So I go up minus IB minus IA times 40. Then I go to here minus IB times 8. Then go to here, there's nothing. Go to here, there's nothing. I come back, I need to equate it to 0. So you expand and simplify this, you should get 40 IA minus 48 IB equals to 0, right? So this is your second equation. Two equations, two unknowns. That means if you solve 1 and 2, you should get IA equals to 3.6 and then IB equals to 3. Well, IA doesn't matter, right? Because what are we interested in now? We are interested in the short circuit current. So let me go back to this diagram. Our short circuit current is the current through this branch, correct? And that means IB is the short circuit current. So the value of IB is the short circuit current. So what this means is ISC equals to 3 amperes. So final step. Quickly, tell me what's the final step in the chat. Final step is, let me look at the chat. R Thevenin, right? So R Thevenin, you just take the answers from the first two steps. So R Thevenin equals to V Thevenin divided by short circuit current, which is equals to so our Thevenin resistance is 48 divided by 3. This should give us 16 ohms. So this is our Thevenin equivalent resistance. Now, to find the... Actually, in this question, I'm asking you for the Norton, right? Okay, so it doesn't matter. Remember I said the Thevenin resistance is equals to the Norton resistance, which is 16 ohms, right? And then just now, I want the I Norton, which is equal to the I short circuit, which happens to be 3 amperes. So if I want to change this into a Norton equivalent circuit, I take this, the current source, connect it in parallel to the Norton resistance, which is 16 amperes, and this one is 16 ohms, 3 amperes, and this is A, this is B, right? This is the Norton equivalent. But we might as well discuss the Thevenin, right? It's not so hard. So we already know that V Thevenin is 48. So if I want the Thevenin equivalent will look like this. It will look like this, connected in series with the, again, also 16 ohms. Yeah, 16 ohms. And then this is A, the B, and then the Thevenin, this is 48 volts. Like that. So this one will be the Thevenin equivalent. And additionally, I'm just going to go ahead and recap on the max power transfer. So max power transfer, the formula is, I want you to tell me the formula now. What's the formula for max power transfer? Anyone? V squared over 4 times R Thevenin. Okay, V Thevenin. Okay, remember it's V Thevenin. Okay, so thank you. Who is that to tell me? Okay, thank you, Hamza. So max power transfer is given by V Thevenin squared divided by 4 times R Thevenin, which is equal to, now the V Thevenin is 48 squared over 4 times 16. Now I didn't calculate this, so just go punch in your calculator and that answer should be in watts. Okay? And that's it. Okay, so that's pretty much the end of equivalent circuits. Now, remember I told you that the Thevenin resistance and the Norton resistance is just the total resistance of the circuit. And we know this concept from, I think, secondary school, right? Remember, we are always told, oh, for the total resistance in series, we use this formula. Oh, okay, wait, sorry. R1 plus R2 plus R3, blah, 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 blah. And then if they are parallel, sorry, 1 over R parallel, we use this formula, 1 over R1 plus 1 over R2 plus blah, 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 right? To find the total resistance of the circuit is just finding the Thevenin or Norton equivalent resistance. That is what we're doing all along. But, okay, you want me to prove it to you? I'll prove it to you. So let's try this circuit over here that I draw. So, how to find the resistance using the old-fashioned secondary school way? So, to do that, the steps we need to do is this. Whenever you see a current source, you need to open circuit it. Whenever you see a voltage source, you need to short circuit it. Now, in this case, we have a voltage source. So let's short circuit it. So I'm going to redraw this diagram. When I redraw it, sorry, let me take a picture with my phone so that I can use it as a reference. I don't like to go up and down, up and down. Yeah. It just, oh, let me see if there's any message. Max Verstappen. Okay, I don't know what is that. Okay, so remember at the side, at the very left side, right, there was a voltage source, but now I'm gonna replace it with just a piece of wire, just short circuit it. And this is the 10 ohm. Everything else I just copy. So this is 40 ohms. Then over here like this, this is 8 ohms. And we want to find A and B. So if I'm looking through A and B, what is the total resistance of this configuration? Now, let's just use the classic formulas that we know. So let me ask you this, 10 ohms and 40 ohms, are they in series or parallel? Tell me in the chat. They are. Okay, Vishnu says parallel. Anyone else want to try? You have 13 people, okay. Vishnu says parallel. Anyone else want to try? Hamza? Okay, Hamza says series. Weekend? Brian? Ain? According to the lecture slides, it's parallel. Oh, I didn't really know the lecture slides cover this. I didn't get this from the lecture slides, but okay. See, Ain says it's parallel. Brian says it's series. Okay. I'm glad I conducted this poll. Otherwise, I would have assumed everyone knows. Okay, so the answer is they are parallel. Okay, these two are parallel, 10 ohms and 40 ohms. Now, why is that? Look at this. This is one node, right? This is one node, right? If the device is connected to the two same nodes at their two terminals, right? The terminal of this is over here, right? This one is connected to this node. And then the terminal at this end is connected to this node. But for the 40 ohms, this terminal is connected to the same node. This terminal is also connected to the same node. So since both their terminals, both of them are connected to the same exact nodes, right? They have to be parallel. They have to be parallel. Now, if you find this confusing, okay, at least everybody knows that these two are parallel, right? Yeah. So if you want to reimagine this, I can kind of move this resistor down here, right? I make this segment of wire longer. This one make it longer. And then this one, I make this shorter, right? Then it become more obvious that it will look like this. So let me just redraw it. It will look more obvious that it looks like this. This is 10 ohms. This is 40. Then what else? Over here is 8. And then these are terminals A and B. Okay, now can you see that these two are parallel? Yeah, these are parallel. Parallel. All right. Having said that, now we can find the now what I want to do is combine the resistance of 10 ohms and 40 ohms using the formula, right? Using this formula, 1 over R para equals to 1 over R1 plus 1 over R2. So if I do that, 1 over R para equals to 1 over 10 plus 1 over 40. R para is 8 ohms. Okay, you can punch your calculator, you should get 8 ohms. So when I combine these two together, group, I merge this together, it is just like saying I put a single resistor, only one resistor of 8 ohms. 8 ohms. And then everything else remains the same. So this one over here is 8. This is A, and this is B. So now these two, this 8 ohms, are they series or are they parallel? Okay, Sherman says series. Anyone else? Vishnu, Samuel, Hao Liang, Ain, Hamza. Who else? Brian, what are your answers? Okay. So Vishnu says series, Sherman says series, Hao Liang says series, Hamza says series. Samuel says series, Ain says series, we can say series. Okay. The overwhelming majority of you, yes, you are correct. It is in series. So I think this is clear and obvious to everyone, right? Samuel, you said, but why though? Did I answer your question? I think you were asking about the parallel, right? Let me see if Samuel's okay. Samuel, all good? Okay, good. Okay, so I'm gonna recap to see whether they are technically, by the technical definition of what is parallel, you check, are they connected to the same nodes? See, they're connected to the same nodes here, same nodes here. So they're parallel. That's what it means. Okay, otherwise you eyeball it using your secondary school idea of what a parallel configuration is. Okay, so now that I know these are in series, I just add them up. So R total equals to 8 plus 8, which is 16 ohms. And then remember earlier we got this 16 ohms here. See, using the whole find the open circuit voltage, find the short circuit current, and then take open circuit voltage divided by short circuit current, we get 16 ohms. And then using the whole secondary school way of using the formulas, the formula of total resistance in parallel, total resistance in series, we also still get 16 ohms. And that is what I'm trying to tell you. The Thevenin resistance and the Norton resistance, at the end of the day, it is just telling you the total resistance of the circuit. But of course, we are not going to use the secondary school method ways to find the total resistance, right? Why? Because it is so complicated. Some configurations are so complicated, you don't know whether it is series or parallel. Look, I gave you quite a simple circuit, right? Honestly, this is considered a very simple circuit. But when I ask you whether it's parallel or a series, some people don't know, right? And it's not your fault. It's not easy for me too. You ask me, right? Sometimes I also tell you, I don't know. It really is that hard to tell whether they are parallel or series. Yeah, I have some friends who know how to do that, but well, I guess they're gifted, I guess. But no, you're not weird when you don't know how to tell whether they're parallel or series. It is quite hard. And that is why we prefer to use Thevenin and Norton to find the total resistance. Okay? Yes, you can find the total resistance for any circuit using the find the open circuit voltage, short circuit current, take the first answer divided by the second answer, and you will get the total resistance. This is foolproof, okay? That is one way you can find the total resistance, is by finding the Thevenin resistance or the Norton resistance. Okay? Yeah, that's what I wanted to say. All right. I guess that's it. It's really it. Yeah. The next chapter, I don't want to step on capacitors and inductors yet. Yeah, because why bother, right? And what I have is these questions that I skipped. So I didn't work this out yet, but I guess I will work this out and send you the answers. So I will work this out. I will send you the answers. And then, yeah, so these are, I guess, meant to be homework for your homework. You can find the equivalent. You can find everything, right? There's always three questions that I can ask you: Thevenin equivalent, Norton equivalent, and the max power transfer. So do that for this question and also this question, and I will upload the solution for you on the Teams, and that's it. You really can go already. You don't have to stay until 10. Yeah, I can just end the class early here. So if nothing, you all can leave already. So Vishnu asked, so we just followed the 3 steps instead of secondary school method. Yes, Vishnu, you really can just find this, find the total resistance using all these 3 methods. But I will admit one thing, it is very tedious, right? You have to do mesh current analysis twice here. One for step 1 and one for step 2. It is quite tedious, honestly. But I tell you, it's foolproof. Why? Because there are some questions, right, which ask you find the total resistance of this configuration. But I don't know, using like the normal formula ways, I don't know whether they are series or parallel. And if you don't know whether they're series or parallel, well, you don't know which formula to use, then bye-bye. So yeah, that's why I prefer to stick to just follow these 3, you'll never die. You really will never die. So if we are asked to find the Norton, do we find the Thevenin first? Yeah. Actually, you are just, while you are executing the 3 steps, right? Those 3 steps will inherently have the answers for the Norton equivalent. Okay, let me recap the 3 steps. Number 1, open circuit voltage. This will give you V Thevenin. Number 2, this is short circuit current. Which is ISC. Number 3, we take the R Thevenin is equal to V Thevenin over ISC. Like this, Samuel. Yes, you can technically just follow the Thevenin method to find, okay, you can find the method to find the Thevenin equivalent. That will automatically give you everything you need to know about the Norton equivalent. Why? Because the short circuit current here is indeed the Norton equivalent current source. And then this R Thevenin here is indeed the Norton equivalent resistance. Okay, you can just take this answer divided by, yeah, here, and then this answer is actually here. Yeah, so this method, right, kills 2 birds with 1 stone, right? It kills 2 birds with 1 stone. You can find both the Thevenin and the Norton using these 2 methods. They will inherently give you the values you need to find both Norton and Thevenin. Okay, Samuel, do I answer? Okay, wait, Samuel says, then to be honest, what's the difference if they are essentially the same? Okay, for practical purpose, right? Some people want to view some things as a current source. Some people want to view things as a voltage source. So don't need to worry about this. In the finals, nobody will ask you, okay, what's the difference? It's just like that. Some people prefer to look at it as a Norton equivalent, which is a current source, is a circuit driven by a current source, or some people want to think of it as a circuit driven by a voltage source. Yeah. So Yeah. I hope I answered your question, Samuel. Really, there's no difference, honestly. It's just the way we try to simplify it. Okay. No problem, Samuel. So if y'all don't have anything, I can just let you go. Yeah. This is an early class. Because in fact, I cover more than what we can, right? Supposedly by next week, we're supposed to cover max power transfer. But max power transfer is so easy. It's just that one formula. P max is equals to V Thevenin squared over R 4 times R Thevenin squared. It's just that only. That's why I can just cover it here. Yeah, in fact, we are faster than usual. So if you want to go, it's okay. You can just go ahead because the class dismissed already. Hey, no problem, Hamza. See you, see you. Okay, see you. Okay, Vishnu is gone, but see you, Vishnu. Okay, bye bye, Sherman. Thank you for coming. Okay, bye bye, Haliang. Thank you for coming. Max Verstappen is the F1 driver. Oh, okay. I didn't know that. I'm not a F1 fan. Samuel. Yes, love you too. Love you too, Samuel. 2 times WTC. I don't know what that is. What's WTC? World Driver Championship. Oh, okay. You all are all F1 fans educating me on the new world. Oh, I stopped recording, stop recording.